But I emailed Haley and had her, she's supposed to be emailing everybody, including the faculty, so.
Okay, that's good. So let me see. So can you see my slides? I don't know.
Yep.
Let me see. Let me go to the correct slide.
Good to go.
Okay, so we're gonna review first. Okay, hello everyone. This is the second session or talk, the tutorial talk about blockchain. Today I'm going to continue my explanation about or the tutorial talk about the blockchain. It depends on the timing. I cannot for sure say if I can finish my slides because now we are starting half an hour late. But I try my best to at least cover the general aspects of the blockchain. There is a lot more than these slides, of course, into the blockchain, but I've tried just to give you some sense of what's going into blockchain technology in general, so you can continue from there. So before going into deep about the security properties and how they are satisfied through the crypto primitives that I explained, I will generally go through the description of the security properties that are used very fast, just to refresh your mind. We talked about the hash function, especially the crypto hash function. We said that a hash function generally is a one-way function. That is, when you give it an input with any size input, you're going to get a specific size output, and the output size will always be fixed. But on top of this, we have a couple of other properties, like you will not be able to extract the input if you know the output of the hash function. It's deterministic. That means if you give the same input twice, the hash will be the same. Also, the distribution of the hash function should be in a way that if you change only one bit of the input, the hash value should completely change. And the second property was the second pre-image resistance. That means if you know a pair of input-output hash value, it should be really hard for an attacker to guess another input which maps to the same out hash value. The collision resistance also means it should be generally even hard to predict, to find two different inputs which map to the same hash value. Which all these three features, especially the one, are some of the fundamental aspects which are considered providing the security in the blockchain. Okay, we also talked about Merkle tree. We said that we are using the binary Merkle tree, that is for your data set, which here is the transactions. Each transaction will be hashed, and then each two hash neighbors will be concatenated, and then again the hash function will apply into it until we reach to a single hash value, which is considered as the root of the hash. Let me see if I can put the chat part. Okay. If anyone has questions, meanwhile, you can put it in the chat and I will answer. And so this is the second security crypto primitive that we talked about. The third one was the digital signature. We said that the digital signature uses the asymmetric encryption, which the keys for encryption and decryption is different. You use the secret key to sign a message, and then whoever has the public key or whoever wants to verify your signature can use the public key, of course, together with the signature and the actual message, and verifies and sees using the public key if the signature maps to the same message that you have sent together with the signature. In the Bitcoin, the public key that you use for your digital signature is considered as your address, but to decrease the size of this public key, because the blocks size are limited, and they use the hash of the public key instead of the public key itself. And the hash of the public key is considered your address whenever you want to mention that you own a cryptocurrency. We also talked about the structure of a block. We said it has a header, it has a body, and the blocks are chained through some crypto primitives. Now we understand what is that crypto primitives is the hash value of the previous block. So the way that the chain is created is whenever you create a block, you compute the hash value of the previous block's header, and you add that hash value into your new block header. And this way, if the previous block value changes, so the hash will change and your current block will change. And in this way, you are creating a chain of blocks together. We talked about the body of the blockchain. We said it contains transactions. Regarding transaction, we said if we apply hash on the transaction, that will be the ID of the transaction. The transactions, we had two types, the Coinbase, which creates a coin from nowhere and is mostly used for the miners who create new blocks, and the normal transaction which you use to transfer money from an address to another one. In the normal transaction, you have input and output. The input refers to the previous outputs, and the output is the value together with the address of the new owner of the digital currency. So now that we have all the primitives, let's closely look inside each block and see how the blockchain is using these primitives and actually works based on it and provides us the security. So in a blockchain, we talked about the body, so I won't talk about the body anymore. In the header, you have the Bitcoin version number. I'm explaining the blockchain based on the Bitcoin, but you can consider it for a general purpose. They may slightly be different, but the structure is the same. So you have the version of the protocol, and it's important because this is how the node will know how to interpret the transaction. You have the previous block hash value. As I said, when you create your new block, you have to compute the hash value of the previous block and add it here. This is part of where the immutable property comes from, and we're going to explain it more. You need to compute the Merkle tree root, and we explained how this is happening. You compute per each transaction in your body of the blockchain of your block. You compute the hash of that transaction and the hash of the concatenated of the transaction, and until you reach the root. And the Merkle root together with the previous block hash are the essential part of the immutability that we're gonna talk about it more in detail. So why we only store the Merkle root? Because it's efficient. You just need to store the root. You don't need to store all the other values, but using this root, you can figure out if any transaction changes, the root will be also changed. So it will help you to make sure that the transaction remains, the transaction in the body of that block remains immutable. We also have the timestamp of the block. That means when this block was created, and this is also important, especially for the forks that are created, which indicates the order of the blocks that are being created and added. This is also important to prevent changing the places of the blocks in addition to other primitives that you have. Another important feature or parameter in this block header is the bits. Bits, I will explain it in detail when I'm talking about the proof of work, but it's the level of difficulty that the miner should solve in the proof of work consensus protocol. And these bits or the level of difficulty changes each couple of years, or to talk more accurately, each specific amount of blocks are added to the blockchain. And it's mostly depends on the technology, hardware technology for computation, but they can kind of relate it also to the number of blocks that are being added, and at a specific time they evaluate how the difficulty of the power of proof of work should be. We also have a nonce that is used by the miner to be able to give us the correct proof of work. We also will talk about this later on. Okay, so now we understood the whole structure of a block. It has some header, it has in its header it has some information, and its body it has a transaction. The size of the block is fixed. You cannot go beyond that size. So the miner should be careful which transactions to pick. The miner is free to not pick any transaction, but there is some motivation embedded into the structure of the protocol to make the miner more motivated to pick a transaction. So we also talked about the Bitcoin network generally. So Bitcoin is a peer-to-peer network. That means there is no hierarchy and no node is a special node. All the nodes have the same level, are in the same level, have to share the burden of the work of the network. And this is the structure of the network. So I won't go more into detail, but we have different type of nodes, like full node and other type of nodes, which they will do different works. However, if you want to join a blockchain protocol, you are free to pick which type of node you want to be, but the amount of work that you need to do as a node is no difference. You have to do some specific amount of work if you want to create a block. Now, I think the most interesting part for us, most of us, is to see how a miner or you as a miner can mine or create a block and add it, and what is the consensus protocol which the blockchain is using. So as we talked before and last week, we said the problem that was trying to be solved at that time was, can we have a digital currency without third party and without having the problem of double spending? Here is an explain of the double spending. That means if you have a digital currency, you should not be allowed to spend this money in two different to buy two different products, for example, or at least two different products. So the protocol should prohibit and prevent you to do such an action. And in order to for the receiver of this digital currency to make sure and confirm him or her that the transaction or the digital currency that he is receiving is not a double spended money, we say that the client or receiver should wait for a couple of confirmation. The norm is to wait for 6 confirmation. We talked about the confirmation. Confirmation is when each block is added to the block that of the transaction that you have, you are interested in, is a confirmation. So 6 confirmation means have 6 blocks added to the block that your transaction is in it. And in this way, you will be sure that that digital currency that was transferred to you has not been double spended, and you will have the security and backed up with the blockchain technology that it will not happen. In the future, nobody can probably with high probability can have the enough computation to double spend it or cheat. So what's a consensus protocol, and what does it mean to reach to a consensus? So the consensus in the blockchain technology is slightly different from the distributed system that we, some of you may know. In the distributed system, we say consensus is that all the nodes reach to an agreement, and for this reason, the nodes usually, among the nodes, they have a leader, and if the leader is an attacker or a cheater or whatever, and they will put it aside, another leader will be picked, and the nodes should communicate with each other in order to reach a consensus. However, in the blockchain technology, the consensus protocol slightly different. There are some rules which are called consensus rules, and we say that the network reaches a consensus when all the nodes have the same block in their blockchain, the same blocks in their blockchain. And how you can reach that, excuse me, when you follow the consensus rule, if the consensus rules apply for all the blocks in the blockchain, you will be sure that you are in consensus at that point. So each node will follow the consensus rule separately, and if all the blockchain or all the blocks in the blockchain satisfy the consensus rule, you are sure that you are in consensus with all their network. So here I brought to maintain consensus a full node. All full nodes validate blocks using the same consensus rule. Here, full nodes, I just eliminated a couple of slides. We have different type of nodes. Full nodes are nodes which do a lot of work and to make sure that the protocol is working properly and the blockchain has actually the correct structure. But if we consider all the nodes do the same work, if you join the blockchain, what you have to do at the first point is to make sure that all the blocks in the blockchain are following the consensus rule of that blockchain, of that version, of course, of the blockchain. And then you can go on. So in the Bitcoin example, a couple of consensus protocol consensus rules are like the Coinbase transaction, which is the amount that the miner can receive for the current year, should not exceed the 6.25 for the reward for the miner. The transactions should have current signature, and the input of each transaction should be an output which has not been spent before, for example. The structure of the transaction should be correct based on the data format that I explained before, and a couple of others. And also the block should have solved or had a solution for the computational puzzle, which is the actual proof of work. I call it computational puzzle because I have not explained the proof of work yet. We are not restricted to proof of work, a consensus protocol, which I can explain in a while. There are other type of proof of consensus algorithm which can be used in your blockchain protocol, like the proof of stake, proof of authority, proof of storage. I will explain here only proof of work because I established this tutorial based on Bitcoin, and in Bitcoin proof of work is being used. But other these consensus algorithm, and you can invent your own, of course. These have been introduced later on based on the nature of the blockchain protocol, which wants to be used for a specific structure, for example. But my talk will be based on proof of work. I'll be happy if you want me to explain more about any of them later on. Is there any questions so far? Okay, please let me know if there's any question. So now that we understood that there's a consensus rule that all the nodes will follow to make sure all the blocks are correct, now let's see, we as a miners, if we want to mine a block, how we can do that and how we can get a reward for it. So miners are nodes that are able to apply the mining functionality, okay, that are able to do the proof of work. So can I be a miner? Yes, you just need to download the protocol with this mining function. That's it. So when miner wants to actually create a new block, what it needs to be to do is to make sure that all the transactions that he wants to add in his block are a correct transaction, that the signature is correct, the input refers to an output which has not been spent previously, and so on. So the double spending should be checked, the signature should be checked, everything should be checked to make sure that all the previous transactions are correct. And also the miner needs to create and add a new coin-based transaction to get the reward because of the creation of the new block, and also solve the computational puzzle or do the proof of work. So why the miner takes itself into validating all the transactions that he wants to add? Because if any of these transactions are invalid, then his block won't be added, even if the proof of work is correct, and will be rejected by other nodes. And he doesn't want to waste his energy and all the efforts that he did to add the block to the blockchain and get the reward. So he won't get the reward. So it's important for him to make sure that the transactions are correct and everything inside the block is correct, because as soon as he starts the proof of work and does it, then based on the information inside the block, he will get the reward based on the consensus protocol. So does the miner need to add any transaction to the block? I explained this before. No, he doesn't need to do so. But the reason for him to do is because the transactions usually may have some amount of money that will be given to the miner. And this is a motivation for you, for the miner, to add these transactions. So if you you're doing a shopping and you want this transaction to be added to the blockchain sooner than later, it's better for you to put a noticeable amount of Bitcoin to be reward as a reward for the miner, so the miner get more motivated to add that transaction into its blockchain. And we explained about the miner will receive its reward after 100 confirmation. And we also explained that the coin-based transaction amount will decrease each couple of years, or more accurately, each couple of blocks that are added to the blockchain. Okay, now the very interesting part, which is proof of work. I assume everyone is interested to know how this works exactly, and why even proof of work and what's going on. Before explaining the proof of work, I have to let you know that the proof of work was not originally created by Satoshi Nakamoto in his paper. It was being suggested previously by other researchers for other purposes, but Satoshi also used the idea here. So the whole purpose of proof of work is the miner to demonstrate that he has done a certain amount of work by providing the solution to the computational puzzle. So what's the computational puzzle? He actually has to compute a specific hash value, which is lower than the difficulty that is mentioned in the header. Do you remember I said there's a bits? The bits is a level of the difficulty. So the level of the difficulty is mentioned there is something that by computing the proof of work, the hash that the miner gets through the computation of proof of work should be less than this bit, or the level difficulty level. And this is the hard part. Long time ago in 2010, when or 2008, when the Bitcoin actually was developed, this level of difficulty was pretty low. That means it was much easier for you to compute the hash value, which is less than the bits. But nowadays, as the hardware technology improves, the computation power has increased, and they are increasing this level of difficulty, and I will explain why this is happening. So first of all, the proof of work, as I said, was not originally from Satoshi Nakamoto. Where it came from, long time ago, especially for spam emails, they were thinking how to prevent the spam email spread. And the way they came up is, let's have the authentic person who wants to send an email to ask him to compute a specific hash value, which is not difficult to be computed, but it may take 30 seconds of his time or 1 minute of his time. And since you usually do not send a lot of emails to other people, so 30-second delay is fine for you. But you, as a person who wants to send a spam email, you don't want to send spam email to 10 people. You're going to send spam email to maybe hundreds of thousands of emails. So computing these 30 seconds for the spam email will be great amount of time and energy, and this will demotivate the person to send spam emails. And this was originally the proof of work, which it was the main purpose that it was introduced a long time ago, and later on was used by Satoshi in the blockchain technology or Bitcoin, just to give you some vision about it. But anyways, let's go back to our topic and see how the proof of work works. And so the way that the proof of work works is in this way. Do you remember I said that there is a nonce in the block header? Beneath the bits, the level of difficulty. Here how they do it. After that, the miner added its transaction and computed the Merkle root, added the hash of the previous blockchain, the version and everything. What he is left with is announced that he can change it. What he's gonna do is first, he's gonna calculate the hash of his block and compare it to see if it's less than the bits difficulty. If it is less than the bits difficulty, he is a lucky person and he can publish his block. But mostly this is not the case. So what he has to do is he has to change the input value. But we know that the hash values are deterministic. That means if you get the same input, you're going to receive the same output. So how can he change the input of his block? Because he don't want to change the transactions, because it's really expensive for him to evaluate another transaction and add. In order to solve this problem, instead of, he won't touch any part of his block, only the nonce part. So he's gonna set the nonce to 0, compute the hash value and compare it with bits. If it's higher than bits, so it doesn't satisfy the difficulty, he's gonna add 1 to his nonce and again compute. And since we said in the hash functions, if you change a bit there or something inside the input, the output value will completely change, so you can have another output. And he has to repeat this until the hash of the block, the header of the block, of course, will be less than the bits level, difficulty level. If he gets to that point, then he was able to find a solution for the proof of work or for the difficulty. And he is able to announce and actually publish his block. The way that the hash function works is hard to find out the input for a specific output. This is what we have here. It's really hard to find the input. He has to test all the different nonce to figure out which type of which input will map to this structure of output. But it is really easy to compute if a specific input will map to a specific output, because you just apply the hash function on it. So when I say that my block satisfied the proof of work difficulty level, everyone can easily evaluate it by applying the hash function on the block of my header that I published. And everyone, all the nodes can verify if my block satisfies or provides a solution to the proof of work. And this is how it works. But now a question may come, okay, why we have to use a lot of energy, a lot of power to do so? And there are a couple of reasons, but the most important one is we want to prevent the attacks. So we want the person who is trustworthy peer to do some work to get the reward, and also to prevent the adversaries or attackers to be able to modify the previous blocks. In other words, it's kind of defense against the denial of service and against the tampering, actually changing the structure. Because of the nature of the proof of work. So let's look and explain it by an example. Let's consider that we have these 4 blocks, and the adversary, for any reason, double spending, whatever you want to consider it, wants to change a transaction in the first block on the left side. So the most recent block is on your right side, the older block is on the left side, okay? So what he's gonna do is he's going to change the transaction. By changing a transaction, as you may have expected, the Merkle root will change. Because as I said, all the blocks should be following the consensus protocol, and the full nodes will always try to evaluate all this before starting working or joining the network. So the Merkle root will change. So if the Merkle root changes, that means the hash value of this block that should be added to the next block also will change. So for the previous Merkle root, the hash value of this block was, for example, 9430. Now this hash block should be changed to 4684 because you changed the Merkle root, so the hash value will change. Since the hash value of the second block is changed, now it doesn't satisfy the proof of work with the current nonce. So the adversary should spend at least 10 minutes of computation to find out the correct proof of work for this block. And meanwhile, he's spending 10 minutes to do so, the other peers are also adding blocks to this blockchain. And then by changing this nonce, the block of the second, the hash of the second block will change, and this will affect the third block, and so on. As you can see, for changing one transaction in the fourth previous block, the adversary needs to change all the blocks and do the proof of work for all the future blocks after that. And as you know, the network is continuing, it's not stopping anywhere. So blocks are also being added. So if the adversary wants to win the game, he has to have enough computation power to do the work in less than 10 minutes to be able to reach the speed of the network to create the new block and be successful. But this is something that cost the adversary, the competition is costly. So does it worth it to do that or not? This is the case which creates the immutability of the blockchain. So the cost and benefits that is here should really worth for the adversary to put that amount of computation power or work to do that and to win it. So the whole purpose of proof of work and the 10 minutes of a great amount of efforts is to prevent the denial of service attack and the tampering and double spending, all these. So any questions so far? Everyone understood the proof of work and why we spend 10 minutes. I will explain a bit more about it later on. So, okay, so now a question may raise into your head that what if two miners at the same exact time published a new block? So this will create a fork. A fork can happen for two reasons. First, a split in consensus. That means two miners by chance at the same time create two blocks with the proof of work, even though their transaction may be different, but they have created a valid block and distribute it. Now the nodes should decide which one to pick, which we're going to explain. The other reason for fork may be for changing the version, the rules, and we have different type of forks. I will not explain it here. I will just explain the split of in consensus. So let's consider at some point, two miners were unlucky to publish the same two blocks at the same time. Now the system should decide which one to pick. The nodes actually should decide. And there's a general rule in the blockchain protocol which says always follow the longest path. So here, the longest path for both forks are the same. So this is only a decision which a node makes, a miner makes. So let's consider I'm miner A. I decide to go the above path, and miner B decides to go to the below path. But I was lucky enough to be able to create the new block faster than the miner B. So what happens is as soon as I publish the new block as miner A, which I decided to do it on top of the above path, now my chain my path has longest chain path than the lower one. So the block that was added in the lower path will be eliminated. Nobody will follow that fork anymore. And as you know, we talked about it, the miner will get its coin-based reward after 100 confirmations. So the miner who added his block, the lower block, will never get rewarded, and he was just unlucky. And this is how it works. So the probability of two miners creating two new blocks to the two different paths is pretty low, but the probability of two miners creating a new block for the same block is much higher than the other way to have two kind of. But at some point, a miner will add sooner than another one in one of the paths, which makes that path longer, and everyone will go with the longest path. So I won't go through the details of the changing underlying rules. I have these slides, however, if anyone would like, I can share with them. Now let's go to talk a bit about the mystery of the block time. As I said, it takes you around 10 minutes to add a block with all the power computation that you had. Why is the reason? Because they want to preserve the security of network, as I explained. And the way that they evaluate the timing for creating each block is based on the computation power. They do it after every 2016 blocks are added, which is roughly around each 2 weeks. Each 2 weeks, they evaluate if the difficulty, the bits is enough based on the current network power and computational power or not. So nowadays, if you want to do mining in blockchain, especially Bitcoin, you cannot do it by only having one server or one system. You need to join a pool, which a lot of other computers also are working on the same block with the same proof of work, but they split the nonce between them and do their job, and everyone will be rewarded. The way of being rewarded in pools are different based on what type of pool you are joining. But nowadays, if you want to join the Bitcoin especially, you cannot do it by having only one server. It's better for you to join in a pool. So now is almost 2:05. So I don't know, Harley, should I continue or should we leave it for another time?
I say, I mean, since we started late, we should just keep going.
Okay, so I'll continue and let me know whenever. So I can go up to a couple of slides, maybe one or two. Bitcoin will be done and I will start Ethereum. So if you like, we can have the Ethereum next, but I will not go in deep into Ethereum. I will just want to
Okay, yeah, you would, yeah, we can talk about that after, yeah.
Okay, so let me continue and just stop me wherever you want, okay?
Yeah, so I mean, just go until the point where you think you're finished
So
up.
for the Ethereum, I won't talk a lot because even though it's it's a different type of blockchain, but the building blocks are the same. Just the concept, I will explain in a while. So
Yeah,
I will
sounds
try
good.
to give me some descriptions. Okay.
That sounds good.
So yeah, so we're good with this, and as this is only to show you how the level of the difficulty changed based on the years and the hardware technology improvement, and they will adjust it based on that. So the blockchain, the Bitcoin actually, which is the fundamental knowledge of the blockchain, what's hidden with the description of Bitcoin is done here. Ethereum, however, is another blockchain, but slightly different from Bitcoin, which I'm going to explain it here. Ethereum was proposed in late 2013 by Vitalik Buterin. I don't know if I pronounce his name correctly or not. He's a young cryptographer and researcher and programmer. He actually at that time he saw that the Bitcoin structure, the script of the Bitcoin, was not enough powerful to be able to enable you to develop application. But he tried to discuss it with the Bitcoin developers, and when he failed to gain agreement, he actually proposed the development of his new platform, which was the Ethereum. So the underneath concepts and all the fundamental aspects of Ethereum are the same as the blockchain. The only important difference is that the Ethereum has very rich script language, which is a Turing complete. That means you can write any program using this language. And but with the Bitcoin script, you cannot do that. You are so restricted. And why he wanted this? Because he wanted to actually enable us to develop this decentralized and distributed application. So the Ethereum's currency is called Ether, and in Ethereum, in blockchain, you have addresses, but in Ethereum, you have accounts. So each account may have different addresses and so on. So it's slightly different, but the concept is the same. And here in the Ethereum, you have the Ethereum virtual machine, which does the computation for you. So for the Ethereum, even though the technology is the same, but the building blocks here is the smart contract. What's a smart contract? Smart contract is a piece of code which, as soon as you publish it, will automatically be executed. It will have as any program, it says program actually, which has some conditions. If the conditions are satisfied, some actions will be executed and so on. And this is the fundamental aspect of any decentralized application, which you can, blockchain, which is for the reason of decentralized application. So the Ethereum platform is built specifically to have a smart contract to enable you to develop a decentralized application. Also, since the building blocks of the Ethereum is the same as the general blockchain or Bitcoin, it will provide you with the same security, performance, immutability as the general blockchain that is providing you. So in order to make the smart contract more understandable, I just brought here a comparison and an example. Let's consider that we have 2 users, or even it may be only you with 2 addresses. You have the person A with the address on the left side, it's A0 whatever, which has 10 Bitcoins on the left side, and you have the user B with the address B0 and has 10 Bitcoins. If you wish to transfer a digital currency, you have to use your private key to do this transaction, for example, 5 Bitcoins. However, so the transaction uses the private key. However, if you want to do this with the smart contract, what you're going to have is you have going to have a piece of code. In this piece of code, you're going to have the balance, which can contain some amount of digital currency. You're going to have the account, which is the address of the owner who will receive or the address, which will be the account of the smart contract itself. So you can put money inside this smart contract. You can draw money from it based on the code. And there is a code which replaces the private key that the user, you as a user, use to transfer money. So this piece of code will have some conditions and some actually actions. If the conditions are satisfied, it will execute the actions that are rest. And satisfying these conditions are playing the role of your private key. So when you want to write a smart contract, you will write it, you will evaluate it to make sure that it is correct, it doesn't have any bug, and so on, and then you're going to publish it. So the smart contract actually, or in the Ethereum, the balance or the amount of money is controlled in smart contract by the code. It's also, the code is immutable. Why? Because it has the same structure. As soon as you write the smart contract, you distribute it to the system, and when the system reaches a consensus and after a couple of confirmation, nobody is able to change the code, because you will have the same problem of the proof of work that you had with the Bitcoin example. So this is the same. So it's not like I write a piece of code as a smart contract at some point, I should be worried that someone will change it later on. Nobody can change it. And it's immutable because of the structure of the blockchain. So the smart contract will have the same privilege as the user that created it or assigned to it. And it can receive Ethereum or sometimes Bitcoin, depends on how you want. Some of them are able to transfer digital currency between different type of blockchains. It has some very specific amount and limited storage, which you can store some information inside it. And it's able to execute. It's like the object-oriented programming, which you have different objects and they communicate with each other. So if you want to have distributed application or decentralized application, you have to use, you mostly are using different smart contracts, like different objects, in order to accomplish your mission for creating of that application. So since it has the same structure of the blockchain, the smart contract, when it's distributed among the nodes, it will be replicated in all the nodes, different places. So any change in any transaction to activate the smart contract can be done because all the nodes have a copy of your smart contract. So the way that the smart contract will be activated is if you, as a user, create a new transaction, and in this transaction, you address the smart contract account. You actually call the smart contract account with specific inputs. So if the inputs satisfy with the conditions of the smart contract will be triggered and will be executed. But if not, it won't be. And since all the nodes have the smart contract, as soon as you create a transaction and that transaction is added inside a block, that smart contract will be automatically executed, and your request as a transaction will be executed in that smart contract. However, for each transaction that you send to the smart contract, since it's piece of code, so some computation should be done, you have to pay money for that computation. So the way it works is you need to assign some specific amount of gas. As I said before, in Ethereum, you use Ether as a cryptocurrency, so a gas is not actually money, is the amount of computation you need to execute any smart contract, which you have to specify. And the price of the gas may change. So as one day, a price of one gas may be a specific amount of Ethereum, at another day, it may be different. And the way that the gas price changes, it depends on the demand. If there's a huge amount of demand for people to do computation, the price of the gas will increase. So you have to spend more Ethereum per each gas. And if the demand is low, of course, it will decrease and you pay less Ethereum. So the gas is the kind of the amount of computation you want to spend, and then you have to pay the Ethereum per it. So here comes the tricky part. When you are actually creating a transaction so that to trigger the smart contract, you have to also mention the amount of gas or computation that you want that virtual machine, the Ethereum virtual machine, spent on your smart contract. The way that it works is you may not be sure exactly how much or how much gas you may need. It depends on the amount of computation. So the amount of gas you need to specify should be slightly higher than the computation that you expect, because if the computation goes beyond the gas limit that you have specified in your transaction, and the smart contract has not finished its steps, the node who was trying to execute your transaction does not have enough gas to do it. So all the process will go back and you have wasted your gas. So it's a tricky part. The amount of gas that you need to specify for the execution of the transaction is pretty tricky. If you put it low, then you have wasted your gas and you have not executed the request that you wanted to. If you put it pretty high, you also will have problem. Why are you going to have problem? Because per each block, the miner can only add transactions which do not pass the gas limit of 6,700,000 gases. So if you put a really great amount of gas to make sure that your transaction will be executed, but the amount of gas that is needed for execution of your transaction is 1/10 of your gas limit that you put it out there, and nobody will pick this to put it in the transaction, because the amount of reward that the miner will get depends on the gas that you spend it to execute that computation, not the gas amount that you put. The amount of leftover gas per each smart contract that you execute will return back to you. So there's a trade-off between what will be the gas limit per each transaction that you're doing. It shouldn't be low enough because it won't be executed, but you're going to waste your gas. It shouldn't be high, really high, because nobody will pick your transaction to be executed. So it's kind of tricky here. So hopefully I talked pretty fast, nobody asked question, and I didn't go deeply into the smart contract, but as you may have understood, the smart contract is only piece of code, and since it is published and added to the blockchain, nobody can change it, and it will automatically be executed. And because of this is really interesting. However, since and we saw that it has storage, since all the nodes will have a copy of your smart contract and the values that are stored over there, and also all the nodes will see the transaction that you sent to be executed by the smart contract. So everyone can see the data that you are sending to that smart contract, the owner to whom you are sending currency, what are you doing with your smart contract. The smart contract can be used for development of any decentralized application, like the insurance application and so on. And it is a really powerful tool to do it, but the problem with it is the privacy of it. Since all the data are public, all the transaction owners of the currencies, who receives the amount of money and everything is public, and this is not a good sign for especially private companies which want to preserve the privacy of their customers, like insurance, like healthcare. And here where the smart contract privacy comes into play. And so the current smart contracts generally in Ethereum do not have, even though the Ethereum is working on it, there has been different solutions to preserve smart privacy, but mostly the privacy that they're trying to preserve is for cryptocurrency, not for the smart contract itself. That means if you're trying to transfer the money, but with the smart contract is not only transferring money, you sometimes want to do computation, which you want to preserve its privacy. You don't want anyone except the receiver to know the result of the computation, or you want to preserve the input that the participants are giving to the smart contract. This is the privacy of smart contract. So this is a very interesting area. It's a recent area of research that people are trying to find a solution for it. Of course, as before, there have been some work done in this area, but none of them are perfect, like all the previous works before the Satoshi Nakamoto and all the research after Satoshi Nakamoto of blockchain. And this is one direction of my research, what I'm interested in. There are works being done in this area, and but each of them has their own problem, and we're trying to put the piece of puzzle together and solve one part and have the best smart contract, privacy preserving smart contract. So this is my project that I'm currently interested in. However, I'm really open to any other ideas. If you are generally interested in blockchain, especially after this tutorial, you would like to work in this area, you would like to get more familiar, you have your own idea, you would like to work on it or whatever, I'm really open to it. And if you are also interested in smart contract privacy itself, I'm also open to that. I also work on, since here I have the opportunity to advertise my research, I also work on cloud computing, and especially authentication and part of the cloud. If anyone also is interested in that area, let me know. Thank you very much. Thank you, Harley.
Thank you. It was a very good presentation, and I enjoyed both of them.
Thank you.
Did anyone have any questions before we end the session?
It doesn't seem anyone.
Right, yeah.
So I will give the host to you.
All right. Excellent.
Okay, thank you everyone for coming and joining.
Yeah. Thank you.
And email me if you have questions or anything else. Have a nice day. Have a nice
Thank you
weekend.
as well. Have a good weekend.
Yes, bye-bye. Bye, everyone.